So this is the second of two videos on empirical formula, and in this segment we're going to be investigating some more elaborate examples, some more complex examples, and so I want to equip you with some skills to be able to manage some of the scenarios that you're going to be faced with. So you'll remember that whenever we're finding the formula for, the empirical formula that is, for a compound, then all we're finding is essentially the ratio between two atoms. So I'm going to choose two atoms, X and Y, for instance. And so I'm looking for there to be a whole number ratio. And so sometimes what you'll encounter is something like this, a 1 to 2.98, say for instance. Well, you'll remember that often the information that is presented in an example was collected from an experiment. And so when I look at this data, I think that I'm pretty confident that the 2.98 not being exactly 3 is likely the result of some sort of experimental error. So I'm well within my reason to go ahead and say, well, that's, probably intended to be 1 to 1.3. And then I can go from there to construct my empirical formula. So it would be at 1x for every 3y, so xy3 as an example. Sometimes, however, you are faced with numbers, a non-whole number ratio where you can't right off the bat round up or round down. So let me give you an example of that. An example would be, well, what if I had 1 to 1.5? That's a situation where, 0.5 is exactly in the middle between 1 and 2. So I can't really round. That would not be right to do, not be appropriate to do that. So, when I'm thinking about this, I'm saying, well, in my head, I'm saying, well, 0.5 is really just 1/2. And I know that if I have 2 halves, then I have a whole, right? Half plus another half gives me a whole. So by multiplying by 2, right, 2 halves, I end up with a whole. So that's what I'm going to do here. I'm going to multiply by 2. And remember, in any ratio, whatever I do to one part of the ratio, I need to do to the whole of the ratio. So 2 times 1 is going to give me 2. And then 2 times 1.5 gives me 3. And so here I have a really nice whole number ratio that will allow me to construct a nice empirical formula. Okay, here's a second scenario. Let's say instead I had 1 to 1.25. Now that 0.25 is still not really close enough for me to justify rounding down or rounding up. I can't really do that. And so I'm going to try to get rid of that 0.25. So let's look at the last example to help guide what our decision is going to be here. Well, last time I said, well, I have a half, 0.5 is a half, and so I'm going to multiply by 2 because 2 halves give me a whole. And now in this case, I have 0.25. Now 0.25 as a fraction is 1/4, as you may know. And so I know that 4/4, right, and multiply by 4 to give me 4/4, that will equal 1 whole. So in this case, if I'm faced with a situation where I have 0.25 as part of a ratio, I'm going to multiply both sides of that ratio by 4 in order to eliminate the 0.25. So 4 times 1 is 4, and 4 times 1.25 is 5, and there's my whole number ratio. Now next, I'm going to give you one more example. So let's say I had 1 to 1.3-ish, something around there. Well, 1.3, you may remember that if you have 0.33, that is about sort of equal to 1/3, right? Of course, 1/3 will give you a repeating decimal, but it's pretty close. So I'm going to say, well, to get rid of a 0.33, I'm going to multiply by 3 because 3/3 give me 1 whole. Right? So there I go. So 1 times 1, oops, sorry, that's a 3. That should be a 3. So 3 times 1 will give me 3, and 3 times 1.3 will give me 4. So now I would have a nice whole number ratio with which to construct my empirical formula. All right, let's tackle a second example. So I'm just going to read through it with you. So we have a 5.438 gram sample of lead dolomite. It's a grayish blue mineral, sometimes used in ceramics, and it was found to contain 2.549 grams of iron, 1.947 grams of oxygen, and 0.9424 grams of phosphorus. What is its empirical formula? All right, so in the first example, I gave you some steps, some suggested steps to help you work through this problem, to navigate it. And you'll remember that the first thing that we did was we were given percents in the questions, and so we assumed that we had 100 grams of product, and that allowed us to easily work out what the mass of each material was that we were working with. In this case, we don't need to do that, because in the question itself, they're giving us masses. So we're going to use the masses that they're giving us instead of having to work with percent. So this is actually saving us a step. So let's write some of that out. So I know that the mass of iron happens to be 2.549 grams. I know that. And I know that the mass of phosphorus is 0.9424 grams. And lastly, I know that the mass of my oxygen is the 1.947 grams. So there's my first step. Now I want you to think about what the next step was. What did we do next? Well, in the next step, we converted each of our masses into moles. And so I'm going to figure out what the number of moles is of iron, and I'm going to ask you to figure out the number of moles of phosphorus and oxygen, and then you'll be able to check your answer with mine. So the number of moles of iron I can get by taking the mass of iron and dividing it by the molar mass of iron. Right? So that would be 2.549 grams divided by 55.85 grams per mole for iron. So the number of moles that I have of iron, and I'm going to have to work that out, and that gives me 0.4564. And so I'm going to carry a couple of extra digits here. Oh no, actually that works out for sig figs, so I'm going to leave that. 4 sig figs should be where my answer, the way that my answer should be written. All right, so go ahead, take a minute, pause the video, calculate the number of moles of phosphorus and oxygen, and when you come back, I'll have done the same and we can compare our answers. All right, so I want you to take a minute and examine the answers that I got for the number of moles of both phosphorus and oxygen. I got the moles of phosphorus were 0.0304 moles, and the moles of oxygen were 0.1217 moles. Hopefully you did okay with that. Now I think we're ready to move on to the next step. So step number 3, this is our third step here. Remember, this is a stage where we're going to create that whole number ratio. So to solve this problem, to figure out the empirical formula, I need to know the ratio of iron to phosphorus to oxygen. And so I'm going to need to take a sneak peek here because I can't remember what our number of moles of iron were. 0.4564. 0.4564. 0.4564. All right. And so now I'm going to just put down my moles of phosphorus as 0.0304. And then my moles of oxygen, 0.1217. And so you'll remember that, I can't create a formula with these decimals. I need to get this ratio into whole numbers. And so I'm going to seek out the value in my ratio that is the lowest, and I'm going to divide each of the numbers in that ratio by that value. So my number of moles of phosphorus is the lowest in number, so I'm dividing each of the values in my ratio by 0.0304, and that's going to reduce that part of the ratio to 1. Okay, 0.0304, 0.0304. Okay, so let me just clean this up a bit. I'm going to move this, and then I'm going to create a situation. Let me just move this whole thing up. So now I'm going to keep going. So when I work each of these out, I'm going to go ahead and work these ratios out. So I know I have a 1 here. And I go ahead and I calculate 0.12, oopsies. So when I work out this last ratio, 0.1217, divide that by 0.0304, I am getting the 4.00 and a bunch of decimals. So I feel pretty confident that I can write that as a 4. And I just recognized right now, and you probably noticed a while ago, that I've forgotten a 0 in here. So it should be 0.04564. And when I work that out, I get a 1.5 as my value. So right now I'm sitting with a ratio of 1.5 to 1 to 4. And of course I can't really work with that to get an empirical formula. And so what's my solution? Well, in an earlier example we saw that to get rid of a 0.5, I need to multiply every part of my ratio by 2. So 2 times 1.5 will give me 3. 2 times 1 will give me 2. And 2 times 4 will give me 8. So now it looks like my formula is Fe, I have 3 Fe's, so Fe3, P2O8. And that seems like a reasonable empirical formula. If we think about it, and I go ahead and I take this part right here, it's really like saying PO4 times 2, right? And then I still have my Fe3. And that's a formula that makes sense because I know phosphorus has a charge of -3 as an ion, and that 3 down there makes sense. And I know iron can possibly have a charge of 2, so that this is a formula that makes sense. So this empirical formula is in keeping with what we know about chemistry. So that's a good way to sort of verify if you're on the right track. All right, so I would like for you to try this next question on your own and see how you do. Pausing the video to stop and try it out, write it out. And when you're ready to take it up, then you can take a look at my solution. So propane is a hydrocarbon that is used as a fuel in barbecues and some cars. A 26.80 gram sample of propane, in a 26.80 gram sample of propane rather, 4.90 grams is hydrogen and the remainder is carbon. What is the empirical formula of propane? So pause the video now, give the question a try, and if you're struggling, then play along. But I'd like for you to really give it a good try and then watch the solution when you're done in order to check your the empirical formula that you end up with. All right, so the first thing that I want to do is I want to examine the information that I'm given. And so I'm given the mass of hydrogen, and so I'm going to write that out. So I'm not given percentages, so I don't need to deal with that at all. My mass of hydrogen ends up being 4.90 grams. And so they don't give me the mass of carbon straight away, but I do have enough information to sort that out. So the mass of carbon is going to be the difference between the total mass, 26.80 grams, and the hydrogen. So if I know that the remaining mass is made up of carbon only, and I subtract the 4.90 grams of hydrogen from that, then the remaining amount should give me the amount of carbon, and that works out to be 21.90. And I'm preserving that decimal because remember, with significant digits, I need to look at the number of decimal places, and I have 2 decimal places with both of these values, so my answer should also have 2 decimal places. The next thing I need to do is I need to convert each of those values, those mass values, into mole values. So the number of moles of hydrogen is going to be equal to 1.01, 4.90 rather, grams divided by 1.01, which gives me 4.85 moles. Then I'm going to do the same thing with my carbon. So the number of moles of carbon is going to be equal to the 21.90 grams of it that I have, divided by the molar mass of carbon, which is 12.01 grams per mole. And I'm getting 1.823 moles. And so I'm preserving 4 sig figs when I look at both of the values being used in the calculation here. I have 4 sig figs, so my answer should also have 4 significant figures. So the next part of my solution involves dealing with this ratio, this mole ratio that I now have, right? So my goal is to get the empirical formula, so I need a ratio between the carbon and the hydrogen atoms. Let me write that out a little more nicely. There we go. And so it turns out that I have 1.823 moles for every 4.85 moles of carbon versus hydrogen, respectively. So my next step is to divide by the lower of these two numbers. So I'm going to divide by 1.823 on both sides of the ratio, 1.823. And that will give me a ratio of 1 to 2.66. Ooh, that's weird. So I'm curious to see how you navigated this because we didn't discuss it outright. However, I'm going to just do a little bit of a snippet on the side over here. So 0.66, I'm not sure, do you know what 0.66 is as a decimal? You maybe recognize that as 2/3. And so if I say 2/3 times 3, then that will give me a nice whole number because you see these 3's will cancel and I will get 2. And so if I have a 0.66, I'm going to multiply by 3 to get rid of that 0.66. When I do that, I get a 3 to roughly 8. I'm getting 7.98. That's safely roundable to an 8. And so this is telling me that my ratio is 3 to 8. So now moving that up a little bit, I'm now ready to take my final step, which is to write out that empirical formula. I know that I have 3 carbons for every 8 hydrogens. And so I can say, therefore, this is the empirical formula. And I'm done. So hopefully you did okay with that. And if you didn't, if you weren't sure how to navigate that last little bit with the 2/3, with the 0.66, then that's totally fair. Hopefully it makes sense to you when you see it. I'm going to encourage you now to do some extra practice. There's some extra practice questions posted in our Google Classroom, folks. So take the time to work through those. They do get more challenging as you work down the list. So make sure you don't leave off the last few on the list. And if you have any questions, as always, make sure that you come and see me for some extra help.